The objective of this topic is to explore the physical characteristics of aluminum and to provide you with guidelines for selecting filler metals and for producing quality aluminum welds.
We'll examine the 7 major series of heat-treatable and non-heat-treatable aluminum alloys. We'll explore the physical characteristics of aluminum and the problems they present for welding. And we'll explain the key considerations for selecting electrodes.
Aluminum is popular because it's so much lighter than steel. It also has excellent corrosion resistance and good strength depending on what it's alloyed with.
Aluminum is commonly used in automotive components, bus, truck, and rail car bodies, highway signs and light standards, and in the aerospace industry.
But aluminum is tricky to weld because it has a hard oxide coating with 3 times the melting temperature of aluminum. The thermal conductivity of aluminum is 6 times greater than carbon steel, so you have to weld at higher amperatures to compensate for the heat conducted away from the weld. And the thermal expansion of aluminum is twice that of steel, which means you really have to be careful of distortion.
Aluminum is a highly reactive metal. As soon as it's exposed to oxygen in the air, it forms a protective oxide coating hundreds of times thinner than a human hair. This oxide coating gives aluminum its corrosion resistance. It also makes it hard to weld.
For one thing, even though aluminum oxide is next in hardness to diamond, it's quite porous and can retain moisture and other contaminants. These break down in the heat of the arc to form hydrogen gas, and hydrogen is extremely soluble in molten aluminum. So you have to make sure that the surface of the metal is free of moisture, oil, and grease, or you could end up with porosity in your weld.
For another, aluminum oxide melts at approximately 3,700 degrees Fahrenheit or 2,050 degrees Celsius, while aluminum melts around 1,220 degrees Fahrenheit or 660 degrees Celsius. If you try to weld with the polarity set to DCEN, the aluminum melts before the oxide. The puddle forms under the oxide coating, preventing the molten aluminum from fusing properly to form a sound weld. Compare this to the bright, shiny puddle produced with alternating current.
The arc shows that during the positive portion of the AC cycle, while current is flowing in the direction of the electrode, ions bombard the surface of the negatively charged aluminum. The sparks are actually tiny pieces of aluminum oxide as it's blasted away by the ions. This is called cathodic bombardment or cleaning action. Brushing with a stainless steel wire brush immediately before welding is always a good idea when you're working with aluminum because it helps break up the oxide coating.
The Aluminum Association uses a 4-digit classification system to identify the different types of aluminum alloys. The first digit indicates the major alloying element. For example, the 1000 series is considered pure. They're used in electrical buses because of their high electrical conductivity, and in the chemical industry because of their corrosion resistance.
The 2000 series is alloyed with copper. They're commonly used in aerospace because of their high strength.
The 3000 series contains manganese. These alloys have excellent ductility and moderate strength. They're commonly used for radiator heat exchangers, spouting, aluminum siding, and beverage cans.
The major alloying element in the 4000 series is silicon. This series is used for filler metals because silicon lowers the melting point and increases fluidity.
The 5000 series alloys contain magnesium. Magnesium gives them good strength and corrosion resistance and makes them well suited for use in boat hulls, truck bodies, bridges, and other highway structures.
The 6000 series contains magnesium, like the 5000 series, along with silicon, which gives them the added feature of being extrudable. These alloys are also used in structural applications, often in conjunction with 5000 series alloys.
And the 7000 series is alloyed with zinc for high strength. They're used in aerospace and automotive bumper systems.
Each type of aluminum falls into one of 2 categories, heat-treatable or non-heat-treatable. The heat-treatable alloys include the 2, 6, and 7000 series. These alloys acquire their strength from heat treatment. They'll crack if you try to weld them without filler metal. And heat-treatable alloys above 7039 are not recommended for welding at all. Also, high heat input and the use of preheat will cause loss of strength and cracking in the fusion zone along the toes of the weld.
Typical procedures for welding the heat-treatable aluminum alloys involve the use of filler to prevent cracking. lower amperages and faster travel speeds to minimize heat input, and maintaining maximum interpass temperatures on multi-pass welds to prevent overheating.
The non-heat treatable alloys include the 1, 3, 4, and 5000 series. These alloys derive their strength from strain hardening, also called cold working, and the strength of a particular alloy depends on its major alloying element, silicon, manganese, or magnesium.
So, when you weld the heat-treatable alloys, you're creating a partially annealed condition in the weld and in the heat-affected zone. This means that welds will have excellent ductility, but they'll also be slightly weaker than the unheated metal. Non-heat-treatable alloys can be welded with or without filler metal.
Filler metals for aluminum are classified by the American Welding Society using the same 4-digit system that the Aluminum Association uses to classify aluminum alloys. So ER4043 filler has the same composition as 4043 base metal.
Unlike filler metals for carbon steels that are normally selected based on tensile strength, aluminum fillers are selected based on the application and service conditions of the weldment. So, for each type of base metal that you're welding, you have to focus on the most important characteristics of the finished weld.
For example, let's say you're welding 6061 aluminum, which is high in magnesium and silicon. If strength, ductility, or color match is the major concern, you'd use a 5356 filler. If corrosion or cracking resistance were your major concerns, you'd select a 4043 filler. The Aluminum Association, as well as aluminum manufacturers, can provide you with information on weldability and filler metal selection.
To produce a quality aluminum weld, you need a steady hand and good technique, with a properly rounded electrode and just enough cleaning action to remove the oxide coating, but no more. The molten metal should flow in along the toes of the weld, creating a smooth transition into the base metal. Always use the dip technique on aluminum.
You can't use the lay wire technique because the molten filler will prevent the cleaning action from removing the oxide coating at the root of the joint, and you'll end up with linear oxide inclusions.
A good weld should be clean and bright with an even ripple pattern and a consistent width along the entire joint. The edges of the weld should have a smooth transition into the base metal, indicating complete fusion, and a white line along the toes of the weld tells you that the oxide coating has been cleaned away by the arc. The weld should penetrate completely and evenly to the root of the joint.
A wide flat weld with excessive undercut indicates too much amperage. You can control this problem by increasing your travel speed and reducing the current as you progress along the joint to compensate for heat buildup.
Remember that heat travels quickly in aluminum, so you have to pay close attention to amperage in order to minimize loss of strength and to prevent burn-through, especially on thinner material and on open root welds.
Welding with the amperage too low or traveling too slow causes the weld metal to pile up, resulting in overlap and poor penetration.
Traveling too fast produces a narrow, irregular weld with incomplete penetration into the root.
Too long an arc length produces a wide, flat, irregular weld with incomplete penetration.
A dark weld with porosity indicates insufficient shielding. This could be caused by too long an arc length, insufficient gas flow, damp gas, dirty base metal, or a contaminated electrode.
Longitudinal cracks in the weld or along the toes can be caused by the mismatch of base and filler metals, insufficient shielding, excessively concave fillet welds, or too small a weld bead for the base metal thickness.
Crater cracks are caused by not filling the craters sufficiently at the end of the weld.
You should get into the habit of brushing aluminum with a clean stainless steel wire brush before welding to break up the oxide coating. And you should watch for a bright, shiny puddle with white lines along the toes, indicating good cleaning action.
A final word about aluminum. It doesn't change color when it gets hot, so you can give yourself a bad burn if you're not careful, especially if you're not used to working with it. So don't pick up a piece of aluminum without checking to see if it's hot first.